once more. Hello, everyone. Thank you all for joining us today. Today we have our fourth MOFspace webinar, and it's great to see such strong interest from our community once again. I would like to remind you that the MOFspace webinar series is an initiative of Cost Action EU for MOFs, created to bring together researchers, students, and industry professionals working on metal organic frameworks. So our goal is to share knowledge, to spark discussions, and strengthen collaboration across our field. And by the way, if you happened to miss one of our previous webinars, so don't worry, you can find all of them on our YouTube channel, and you are very welcome to visit our YouTube channel and enjoy the recordings anytime. Okay, so I think it's time to start, it's my great pleasure today to present our speaker, Dr. Pablo Ayala. Dr. Ayala completed a joint master's degree between the University of Vienna and the Vienna University of Technology in 2020, where he began his research in the group of Professor Dominic Eder, working on heterogeneous single-site photocatalysis for hydrogen production. He then continued with a PhD in the same research group, focusing on titanium-based MOFs for energy and environmental applications. His work has led to several impactful contributions, including a major publication in Advanced Energy Materials, and I'm sure that today we will hear some results from this work. Dr. Ayala also completed a research stay at the University of Valencia and received the Best Poster Award at EuroMOF 2025. And now he continues as a postdoctoral researcher in the Eder Group. His work focuses on designing and understanding photoactive MOFs for sustainable technologies, including hydrogen production, water purification, and even niche areas such as tribology. His interests also include exploring higher dimensional secondary building units, modulated synthesis strategies for novel MOF structures, and photocharging materials. So, Dr. Ayala, we are very happy to have you here with us. So the floor is yours, so the screen is yours, please.
So thank you, Alessia, for the very kind introduction. And thank you to the organizers as well for giving me this opportunity. I'm really happy to be here and be able to talk a little bit about titanium MOFs and how we have been using them for photocatalysis and some other applications. For a previous talk, I asked ChatGPT what a future sustainable city would look like. And it came up with this image, which I find quite useful because you can recognize quite some elements here. So first, you can see that there is some solar panels, so probably some clean renewable fuels or energy sources will be in this future city. You also see the river in the center, so we have clean water as well. And you see a lot of very efficient processes happening, so transportation, the wind power turbines. And today, I would like to tell you a little bit about how we have implemented titanium-based MOFs in some of these applications. So this first slide will accompany us throughout the webinar. So I will start by introducing titanium-based MOFs and then go into some of these applications and how we use titanium-based MOFs on each of them. So to start, I think most of you are aware that there is a plethora of MOF structures, over 100,000 described to date. But perhaps less of you know that only a very tiny percentage is titanium-based, so only below 0.1%. And since we are a European network, I thought it would be nice to show where titanium MOFs have been discovered in Europe. So very strong, and I think most people might know this. Paris, Christian Serres' group has discovered many titanium MOFs of the mill families. Now these materials are called MIP because it's a new institute called IMAP. Spain has also contributed with the discovery of a few MOF structures, especially Valencia and Madrid, with materials of University of Valencia and the IMDEA energy frameworks coming from Madrid. And maybe a bit less known are the COK materials coming from Belgium, from KU Leuven. Still, however, as you might see, it's quite few groups that have specialized in describing new titanium MOF structures. So the question is why? Why are there so few titanium MOFs described to date? One of the reasons is that titanium precursors are extremely reactive and they are quite prone to hydrolysis. So that makes them very hard. Titanium MOFs are very hard to grow as crystals to be analyzed then. And this has to do with the titanium oxygen bond strength. Still, however, they're quite interesting, and especially for photocatalytic applications. So I would like to say why we are interested in them, although they are so hard to make. Well, one of the key features is that they are hydrolytically stable, according to the hard and soft acid and basis theory. As you know, titanium 4+ acting as a hard acid, usually coordinated by a carboxylate. And here you have the prime example of Mil-125. This was the first titanium MOF described back in 2009. But there are other coordination modes. For example, carboxyphenolates, when you look at this molecule here, dihydroxyterephthalic acid, and also purely phenolates or catecholates, like this triphenylane. The difference here, when we have these carboxyphenolates or phenolates, is that they coordinate through a chelating moiety. So usually attacking the central titanium atom, and you end up with a monometallic center because they chelate so strongly. And this has some impact on the absorption properties, but also on the photocatalytic properties. So maybe we will get to that later. What is also very interesting about titanium MOFs is their redox and photoactive behavior. So what I mean by that is when you illuminate titanium-based MOFs with light, you have a photo-assisted reduction of the titanium 4+ to titanium 3+. And this is especially observed in carboxylates, like it was first described by Ferrey. So this observation has been made since quite a while ago, and you see this color change due to this photo reduction. Another thing that is advantageous about titanium-based MOFs is that you can tune their band gap, so you can make them absorb low energy light. So this tunability can happen through the linker, so either through side functionalizations or through the coordination mode. And we have also shown already a few works here when we used amino functionalization for Mil-125, and we increased the band gap. We narrowed the band gap, sorry. We improved the absorption properties of this material. And now when you have generated charges, you also want to separate them and extract them. So what about this component? This component has to do a lot with structure. So if you think about these structures, to extract the charges, in the case of Mil-125, the charges would have to hop from SBU to SBU to be ultimately extracted. But if you change the structure of the MOF, you can improve this charge separation and extraction. And this brings me to the next slide. So the dimensionality of the titanium oxo secondary building unit. So starting with the simplest, one could have monometallic octahedron as the inorganic secondary building unit, like is the case in these exemplary MOFs, for example, MUV11 or titanium Cat5, this one by Martí Castaldo's group, and this one by Yagi's group. They often result in these honeycomb-like structures, which are layered. But we can also see that we can also have a titanium oxo cluster. Instead of just one titanium atom or titanium center, we can have a cluster of many of them. And you have also some bridging oxygens. And these bridging oxygens are also very important for stabilizing these titanium 3+ charges. So this is also done with carboxylates. We can extend this further to 1D infinite titanium oxo chains or rods, as it has been exemplified in some works, for example, ACM1 and a few others. And one can take this even to the next step and increase the dimensionality to 2Ds, and the result is some titanium oxo sheets that look somewhat like this, and there are some exemplary MOFs here. So why are we interested in this? Because some have reported that this increase in dimensionality of the SBU can help in charge separation and extraction. And so titanium MOFs are rare, but 2D SBU titanium MOFs are even rarer. So actually there's only 2 described to date. There's a third one that is kind of a combination of the 2. So I will just talk about these 2 for now. So first we have IF11 from Madrid. It's this fascinating structure. These are the 2D layers in from the top, and this is the side view. They use squaric acid, which when it gets deprotonated, it can coordinate kind of as a phenolate, and you end up with this colored material. The other structure that has been described is COK47. This is the top view, and this is the side view. In this case, they used biphenyl dicarboxylic acid. It's a different coordination, so we have a carboxylate, and the color is also different. So both these materials have been used for water splitting applications, and we were very interested in COK47 because there is the possibility to control particle size, defect, content, and we wanted to investigate how that has an impact on the activity. So coming to this first application that I want to talk about, so clean renewable fuels, for example, solar hydrogen. Why are we interested in this? Well, as you know, upon combustion of hydrogen, you get energy, and as a side product, you get water. This is, of course, a clean fuel when you compare it, for example, with fossil fuels, because it avoids CO2 emissions. However, this cycle is not closed, since you cannot just regain, under normal conditions, hydrogen from water. It's an uphill reaction. However, with the help of sunlight and a photocatalyst, you can, of course, make this hydrogen fuel cycle possible. In the community, when we observe this water splitting reaction, we look into both redox reactions separately in order to improve each of them, so that ultimately we could build a catalyst that would work for this one half reaction and for this other half reaction. In this talk, I want to focus mainly on the hydrogen evolution reaction, or short HER. So how does it look like? We have here a little video where we have a photocatalyst on a glass substrate. Now we have turned on the light. It's UV light in this case. And what you see here are hydrogen bubbles going up to the surface. So in principle, it looks quite good. Few ingredients: water, catalyst, light. However, in practice, it is a little bit more complicated. So in heterogeneous photocatalysis, we have 3 key steps. So we have our semiconductor photoabsorber, which has a valence band and a conduction band, as you may know. And when we illuminate with light, we generate an electron-hole pair, or excitons, or charge carriers, through light absorption. This is step one. Then in step two, these charge carriers have to travel to the surface. So we have charge migration. The opposite process here being recombination. So if these electrons fall back down, that's recombination. That's something that we want to avoid. Or maybe on the way, they find some recombination center. And this is also something that we want to avoid. And on the third step, there is charge extraction and the respective redox reactions at the surface, of course. So all of these steps can be rate limiting, you should know. And now we want to see how MOFs could help us tackle some of these steps or limitations. So for one, for the light absorption, we could do some ligand engineering. For step two, which is also pretty challenging, we could investigate higher dimensionality SBUs, for example. And for step three, we could add a co-catalyst, which helps us extract the charges better. Usually people use platinum nanoparticles. However, in MOFs, there's a great opportunity if we can design secondary building units that already have a co-catalyst in them, then we might have also better results. But for today's talk, I would like to focus mainly on this charge migration and charge extraction. So step 2 and 3. Good. So as I said, we were investigating COG47. So it was first described in 2019. We have here these titanium oxo octahedra, 2D secondary building units. They are interconnected through biphenyl dicarboxylate, and they self-assemble to form this particle called COG47. So as you see here, they are quite dense. They seem quite non-porous. So actually, there is two ways of preparing them. You can make them defective, in this case, defects meaning missing linker defects, to introduce some porosity. So these were the two synthesis procedures that were described, the one through autoclavation, very classic MOF synthesis, and then you get COG47L, so L for large particle. And if you use microwave irradiation, high temperatures and very short times, then you get COG47S, S for small particle. So we were wanting to have actually a particle that had these two attributes. So we wanted them small because catalysis is a surface process, but we also wanted to have them perfect because we want to avoid recombination centers. And so this is what we did different. We came up with a different synthetic procedure to make a new COG47 particle. It is quite simple. So you mix your metal precursor and your linker. You use a solvent mixture, microwave-assisted synthesis, and after some processing, you get this powder, COG47 iso, because this particle is isotropic in size, okay, and it's non-defective. So the size, the dimensions, we estimated with TEM, and then the perfectness, so here we mean by that no missing linker defects. We estimated through thermogravimetric analysis. Okay, and so some further characterization that I really like about this first publication was these high-resolution images where we see this lighter lamella of the titanium oxo sheets, which are separated by 1.5 nanometers, which is exactly the size of the ligand. Then, of course, we did powder XRD. All particles gave the same diffractogram, but we are maybe a bit more interested in the optoelectronic properties. So with theory and also experiment, we assessed the band gap. So we found out that it's an indirect band gap semiconductor, and that the band gap of COG47 iso was the narrowest amongst all of them, only 2.85 electron volts. This opens up the possibility to use visible light to excite our material. And then also to the band structure, we did some DFT calculations, and we found out that the edge of the valence band is composed of states arising from the carbon atom, and the conduction band from states arising from the titanium atom. So this will be important in a bit. Good, and now to the experiments. So these were our reaction conditions. We use a methanol water mixture, methanol here acting as a sacrificial agent or a whole scavenger. And we also add platinum nanoparticles as co-catalysts to exchange the charges. And here you see the results of all the particles that were investigated. So we see that this isotropic particle was indeed the best performing one under UV light, but also under visible light. And so we gave a few rough guidelines of what would be good for this reaction or in this system. So high surface area was advantageous, not having missing linker defects as well, and having a narrow band gap was also quite advantageous. And importantly, we got an HER rate of 8.6 micromoles per hour under visible light irradiation, which was one of the best performing titanium-based MOFs to date. So then, of course, we're also interested in cycling this material. So we did also some cyclability experiments where we illuminate and then purge and subsequently so. And we saw a slight deactivation, especially under UV light illumination. But we saw that this deactivation was a bit less under visible light illumination. So that is also good and speaks for using this material for visible light applications. And also, of course, stability is very important for MOFs. We saw structural retention, and this one was also better if we did not use UV light, but rather visible light. So great results. And we also wanted to find out a little bit more about the mechanism and why this is so active. We did some PL studies and radical trapping studies. And there's a lot that was done, but just summarizing, we found out that we had a dual excitation mechanism. So depending on the wavelength that we were using. So when we excited with visible light, we had just enough energy to excite electrons from the valence band that was at the linker to the titanium conduction band. So we had a ligand to metal charge transfer, and then for the charge extraction, these two SBUs were helping to get the electrons to the platinum photodeposited platinum nanoparticles to catalyze the reaction. So we had this charge separation, which is what we wanted. And in the case of UV illumination, we were exciting states that were deeper in the valence band. So they were coming from the SBU itself. So we did not have that charge separation. And hence we were more prone to recombination, which was probably what made the material be a bit more damaged when we were using also the UV light. And so this results were summarized then in this contribution already some time back. And just as a take-home message, I would say that this layer structure is very special, and it promotes an efficient charge separation and extraction mechanism. And this is the reason why this material is so efficient under visible light irradiation. So yeah. Now moving forward, where is photocatalytic water splitting today? This is something that, whoops, there's some line here, but okay, let's just ignore it. Let's see, maybe if I continue or go back. Oh. All right, doesn't matter. Let's try to ignore it. Or can I delete it somehow? It's okay. So where were we? The photocatalysis today. So at the moment, people are already investigating some hydrogen production plants at the 100 square meter scale. So this work was published by Kasunari Domen in Nature. So they have this field with panels that are filled with catalysts. This one is not MOF-based, but rather oxide-based, so it's from strontium titanates. There's also some engineering here, but they are achieving quite some stable performance, and they get high purity hydrogen. So the question is, why are MOFs not being used here? And I think the answer is very likely because they are way too less stable. So this is something that is still limiting MOFs, but it's also an opportunity for us to try and make more stable MOFs that have some good absorption and catalytic properties. However, I want to say that maybe the solar hydrogen production is not the ultimate goal for MOFs, but rather maybe other applications that also have to do with photocatalysis. But I think here MOFs might be really superior. So if you remember, we had this effect where we are accumulating charges in the materials. So we have this titanium 4 to titanium 3 transition. And this has been leveraged to do what is called, what is known as dark photocatalysis. So the concept is the following: you charge your material with sunlight during day, and then your material is charged indefinitely. And what you do then is during night, or whenever you want it to happen, you add some stimuli, in this case, platinum nanoparticles, and then you have hydrogen at demand whenever you want it. So I think this controllability is quite interesting, and actually, yeah, the effect of dark photocatalysis has been described already quite some years ago, but it's still interesting, like this publication just showed by Christian Serre and James Duran. And yeah, we're also interested in this. We want to investigate it, and especially what is it that is stabilizing these charges and how we can control the release of the charges. And the other big question is, how can we make it reversible? So when you put platinum nanoparticles, the platinum nanoparticles are stuck there, so you can only use this once. But there are some approaches already in different communities, not the MOF community, of how to make this reversible. So I think this is also an open question that would be very interesting to look into. Yeah, so moving forward to different applications. So also clean water is something that we definitely need for our future sustainable city. It's quite clear. So you know that industrial processes pollute our wastewater, our water feedstock. And a way to decontaminate it is through photocatalysis as well. So we can also use MOFs here. So here in the second application, we are using probe molecules. These are persistent dye molecules that would stay in the wastewater for very long if we don't remove them. We use methylene blue and methyl orange. And what we can see here is that COC47 iso, this particle that we made, was absorbing methylene blue quite efficiently. And after absorbing it, we want to photodegrade these molecules. So we do this with the help of visible light, because we know it's visible light absorbing. And then we follow up the drop in concentration by UV spectroscopy. And yeah, we compared COC47 to other titanium-based materials and saw that it was quite efficient in removing this dye from the water. However, we were still a bit puzzled about the methyl orange dye and why this one didn't get absorbed. And so if you see both molecules, you will very quickly recognize that not only their structure is different, but their charge is different. So this one is positively and this one is negatively charged. So we did some zeta potential measurements, and we found out that our MOF particles have a negative surface charge. So then it becomes quite obvious that if they are negatively surface charged, they will attract a positively charged dye, so a cationic dye. And this was the key. So then to further corroborate this, we use other dyes that were positively charged that had different structures, and we saw that the concentration upon light irradiation was also dropping. So this was quite some nice result to have this selectiveness of positively or negatively charged dyes. And this work was then also summarized in a publication that was led by my colleague, Stephen. And here, maybe a short take-home message. So this negative surface charge was very important in the absorption of the dye, selective absorption, and this enabled then an efficient photodegradation of these cationic dyes. So yeah, these particles were not only defect-free, but they also had ligand termination. Okay, so this is we were learning even more about this material with time. So some further developments in this area of dye degradation. So we want to also design our own MOFs. So there's a new MOF that we are working with coming from TU Vienna. So we want to put our pin on that map, and hopefully we will manage to soon. But it's a synthetic challenge and also a characterization challenge. But here, big thanks to our collaborators in Spain and Sweden. And yeah, what you end up with is a layered honeycomb structure. It's microporous, so it will likely be able to absorb more dye. And the very interesting thing is that it has even a narrower band gap, 1 eV lower than Coc47. So you can use less energetic light to activate it. And yeah, what we saw was it has about 58% absorption capacity, so about 5 times more than Coc47. And it is able to degrade this dye, so the same dye, using visible light, even at 600 nanometers, which would be kind of orange-red light. So not highly energetic light. So I would like to tell you more about this, but it's not out yet. We're working very hard on the comments, so hopefully it will be out soon. So moving forward to the last application. It's good that I still have some time, so I can tell you a bit more about this rather niche application. And what do I mean by efficient processes? So if you think about the combustion engine, it's quite an inefficient engine. And if you see, a lot of the energy input that you're putting into it is getting lost to friction processes. So here we're wasting a lot of energy due to inefficient processes. And these processes are because of friction. So if we can reduce that friction through advanced lubrication, we can have massive energy savings, not only because you use less energy, but also because you might not need to replace expensive parts that also have a high price in their manufacturing. So now I told you a lot about this Coc47 particle and how we can use it. Now let's see how we can eventually destroy it and make a nice lubricant film out of it. So the field of study that investigates this friction, wear, and lubrication processes is called tribology. The experiments look somewhat like this. So this was collaborative work with mechanical engineering. I was also not an expert here, but I learned a lot through this, and it was quite interesting, to be honest. So you have 2 metal plates that rub against each other. And in between, you put your MOF powder. Okay? And so what's the result then? So the figure of merit in lubrication or in tribology is the coefficient of friction, or short COF. I know a lot of you will think about something else when I say COF, but for now, bear with me for the rest of this talk. This coefficient of friction and not covalent organic framework. So what we want to do is we don't want to have a high COF. We want to reduce the COF. Okay, so this is also something that you have to think about. We want to make it very low. And here's an example. So here we have an experiment where we follow up the coefficient of friction. This is unlubricated, so without our particles. And this is when we add Coc47. We can see that the coefficient of friction dropped about 80%. And what you see here is these wear tracks, so where the contact happened. And there you can see that when we use the MOF particles, this wear track is less deep, and it also formed a tribofilm, it's called. It's a film that happened during these tribochemical reactions. And this one is responsible to reduce this friction and wear. Then we did these experiments at different conditions, so either at normal humidity or at dry air, and we saw that humidity played a major role here. So when we had very dry air, the coefficient of friction wasn't as reduced, but when we had normal atmosphere, there was a reduction of the coefficient of friction. So we wanted to investigate that, but you have to think that these wear trucks are very tiny. They are very hard to investigate. So when we did, for example, XRD, we saw that there is a complete amorphization. However, what was key was that we did some EDX and Raman spectroscopy, and we could see when we had the normal humidity, the composition of this tribofilm was that of Coc47. So we had titanium in this wear track, we had oxygen and carbon in this area, this colorful area. But when we had dry air, first, it was a way deeper scar. And second, there was almost no titanium there anymore. So that means titanium got lost and this tribofilm wasn't built. And the other thing, not only elemental analysis, but the Raman spectroscopy showed us that like with Raman, the nice thing is that you can see different areas. So area 1, which is where you see this colorful tribofilm, you could see also the spectroscopic signature of Coc47. But in those other areas, for example, here, you didn't see this spectroscopic signature. So we wanted to understand this a bit further. So we did some simulations in which we are pulling along different crystallographic axes, helped by our theoreticians, of course. And we had dry conditions, so just pristine Coc47. And then we have some water molecules in there, and then we pull along this axis. And what you could see was that when we had water, we had hydrolysis and a deformation and a passivation as well. And this hydrolysis was less energy expensive than when we didn't have any water in there. And also the stress release was better when we had some water. So water was key here. And then we also wanted to see how other materials perform. First, some other MOF materials. So we prepared some sieves or MIL125, for example. They didn't show any good results. And we also wanted to compare some other 2D materials, since Coc47 is a layered material. So some amexines, black phosphorus, wolfram sulfide, and reduced graphitic oxide. And we saw that the best results were achieved with Coc47, which was great. And this was collaborative work that is also published last year. It was very nice working with these two guys. And as a take-home message from this application, I would like to say that this was the first time that MOF was used as a solid lubricant. So usually when MOFs have been used in tribology, they have been used as additives. For some base oil, for example, but this is the first example of MOF being just used by itself. Of course, solid lubrication is kind of a niche application, probably not so much for combustion engines or stuff like that, but maybe some aerospace applications where you cannot have a base oil or a base medium for adding your additives. And second, that we shed some light on the mechanism. So here, what we saw that was this hydrolysis that promote an in situ formation of a stable tribofilm. And this happened through upon amorphization of Coc47. And this tribofilm was responsible for reducing this coefficient of friction by almost 85%. Good. So with that, I'm coming slowly to the end. So I hope I could convince a few of you that for this future sustainable city, we could use titanium-based MOFs. As a final sentence, I would like to say that we just used Coc47 here, but remember there is many titanium MOF structures to be discovered first off, and then also some that are already discovered that we haven't tested in many applications. So just as a motivation there is a lot of work to do, and yeah, your imagination is the limit. And yeah, thank you all for your attention. I'm stopping at the bit short time, but I hope that's good so that we can have more questions. And finally, I would like to give my acknowledgement slide first and foremost to my supervisor, Dominic Eder, who has given me the opportunity throughout the years to be in his group, also our collaborators and my whole group. And finally, to the Cost Action, you for MOFs and the organizers for this nice opportunity to be here and share with you a bit of our results. And with that, I think I would be very happy to answer some questions. There's some extra slides. And yeah, thank you very much.
Okay, thank you, Dr. Ayala, very much for this nice and insightful lecture. It's really inspiring to see how structural design at the materials level can open doors, yes, to such diverse applications. So now we have time for questions. You can raise your hand, unmute yourself and ask questions, please, or you can write your question in the chat and I can read it. Okay, we have, no? Sumanna? So you can unmute yourself if you have a question, please. Yes, Evelyn?
Well, let's start simply with Suman's question then for now.
Okay.
So Suman basically asked on slide 14, because you were just scrolling through, slide 14, why was 2 weight percent platinum selected as the co-catalyst, and what was the platinum precursor used?
Yeah, very good question. So this, the precursor is hexachloroplatinic acid. Okay. And the weight percent, we did some optimization. So we started at, usually you need very little. So we started from 0.2 weight percent and we went all the way up to 5 weight percent. And then you get this classic volcano plot where you see that at around 1.5 to 2 weight percent, you have the optimal platinum amount. This is because you need enough so that you can extract all the charges. But if you have too much, you also start blocking the light. So too much platinum is not good. And you also, from an economic perspective, I would say it's probably better if you can reduce the amount of platinum that you're using. This is also why actually at my master's, I was trying to go into single site photocatalysis. So really reduce the size of these particles to the atomic level. But this is also pretty challenging.
Absolutely, yeah. And also linked to that, also directly next question. So what could we use instead of platinum to make it cheaper? So platinum apparently works, right?
Yeah, platinum works very well because it's a noble metal and it's very good for absorbing protons and then also desorbing hydrogen. So you wanted to have some affinity to protons, and then you also want to not have so much affinity that the hydrogen stays there, but it gets released. So that goes into this, that's this step, right? So the surface reaction. So if the hydrogen just sticks there, it's not good. And platinum just happens to have this optimal spot in the volcano curve as well. However, of course, it would be better to move away from noble metals, and this is also something that we're interested in doing. So just go to some earth-abundant metals, for example, copper or nickel, cobalt as well. These are metals that also work for hydrogen evolution, although not as good as platinum. And this is why designing, for example, that was what I was saying about this co-catalyst design of the secondary building units. Mixed metal SBUs might be very useful here, because then, although the co-catalyst maybe doesn't work as good as platinum, if we have it very much dispersed throughout the particle, we could get similar.
Like doping, right?
Yeah, exactly. We could get better performances. Yeah, and especially this doping for 2D or 1D infinite SBUs is something that is already being done. And I think it's something that has a big potential. So yeah, other non-noble metals would be great. They just don't perform as good. That's why. Yeah.
Okay.
I'm sure there are many more questions, people. Hands up. Ask
we
whatever
have one more question in the chat.
Good.
Maybe let's start from the chat, and after we will. Have you tried to investigate the activity without co-catalyst? Co-catalysts.
Yes. Very good question as well. It's way less. So you really need that co-catalyst to boost the
folks, please
the activity.
Stop painting.
Okay.
Paolo.
How do you paint? I wonder.
There's a common function. I already tested. People just remove what you just paint here. This is a complete no-go.
Yeah, it's okay. It's just a line. But yeah.
Yeah. So far it's only a line, that's true.
Okay, and we have raised hand. I don't know the name, I see just numbers. So please, you can unmute yourself, yes, and ask question.
Okay.
Hello everyone. My name is Okan Glahmagos. Did you hear me?
Yep.
Yes.
Yeah, I have two questions. And first of all, I would like to thank you your nice presentation and for the application of MOFspace titanium. And we see the literature. There are many works based on the photocatalysis, and their works aim to improve the catalytic efficiency. And you mentioned also that there are a recombination process. And could you give another idea to reduce the recombination process? And I see your research. You need to decrease the band gap because you control the electromagnetic spectrum in visible light. And have you any another works in red light or the laser side? And if you have work also another co-catalyst, because titanium and you did some works titanium and its applications, energy storage, fuels, and also tribology. And another question is that I
maybe
can
the first one.
Yeah.
So for the first one, I think so. If I get it correctly, what strategies could be used to avoid recombination, and how can we make to narrow the band gap even further? What we showed in this work was that actually, in this particular case, so I think it's very complicated to have like just a one-liner of how to avoid recombination. But in this particular case, we saw that having these missing linker defects in this structure was very detrimental in terms of recombination center. So we also showed this with theory simulations in the main paper. So yeah, as you can imagine, these particles. So when you're traveling at this to the SBU to the surface, if you have there some reactive site, some missing linker defect, which is usually capped by methoxy groups, that might be a recombination center. So what we did was we tried to make these particles very less defective and also very small, because then the distance that these charges have to travel is also lower, and it's just more probability that they will make it to the surface. Yeah, so I think that was our strategy here. There might be others. Right on the spot, I can think about perfect crystals, having very perfect crystals that have, no trapped states where the charges can recombine. And to the second question about having a lower narrower band gap. So what that means is we want to make the energy between these two smaller so that we can use visible light, for example. And And yeah, this can be done with ligand engineering, as I said here. But the problem is, for example, when you have this very intensely, no, where is it? For example, here, for example, very deep colored materials, those would be in theory great. And when you have phenolate coordination, like here, or some chelating moiety, those are usually very colored. So like NTU9 is deep red, titanium Cat5 is black almost, so they absorb a lot of light. But when you have these kind of coordination, the problem is that you lose on the effect of titanium on this effect. So you don't have this photocharging, you don't have the titanium 4 to titanium 3. So it's all a balance somehow. In my experience, yeah, the carboxylates are better for separating these charges, although maybe they might have not the narrowest band gap. So maybe that answers a little bit the first question.
Thank you so much.
Okay, we have more questions in the chat. So from Fatima, what is the effect of the porosity of the MOF COG47 on the yield of the reaction? And what pore size is recommended for MOFs used in photocatalysis?
Very good question. These were very small pores, and actually we couldn't find them properly, even in the samples that had missing linker defects. So my way of viewing this particle is that it is actually not really porous. And the ones that were porous, that we made porous by introducing the defects, they also didn't show any advantage if you think about these results. So the small was porous, supposedly. So I think for this reaction, at least in my experience, the pore size is not that important. I think since you have very harsh reaction conditions, you have an aqueous environment and UV light or visible light. And usually when you have large pores in MOFs, they are also a bit more wobbly and less stable. And I think simply they might not work that well because they just decompose more easily. However, if you could make very large pores that are also very stable, well, they should be large enough so that protons can diffuse into and that hydrogen can diffuse out. So about the exact size, I wouldn't be sure at the moment, but so big that I think micropores would be enough. Yeah.
Okay, thank you. And the next question from Sayani. Thank you for the great presentation. Is there an optimal defect window for photocatalysis, or does it remain system specific?
I think it's rather the second. In my opinion, it's system specific. There is some other works by us, by our group with MIL125, where my colleague Shaggy Nahdi has introduced this selective ligand removal strategy, where you have two linkers, one being more thermally labile, and then you just heat up the sample, and one linker goes, leaving open some mesopores, and because of defects. And this was shown to be also very important in the case of MIL125, because you have more open metal sites in this case, probably. But this is a completely different MOF, and I think it's rather the second. It's more system dependent, and I think it cannot be said like cannot be generalized like what's the best defect content level. Sometimes you want defects to have these open metal sites, and sometimes they are seemingly unproductive.
Okay, thank you. And one more question. Can we combine one titanium MOF with different titanium MOF or other MOF to make a heterojunction with improved activity or even stability?
Yes, that's ultimately the goal, I would say. Yeah, so if you find, for example, a MOF that is very good at the oxygen evolution reaction, and then another one that is very good at the hydrogen evolution reaction, and you have optimized both separately. You could, of course, make a heterojunction. The question is how to have them with a good interface. But I think in this sense, MOFs can be functionalized, can be surface functionalized, and MOFs would be a great platform to investigate heterojunctions as well.
Okay, thank you. More questions? Okay, we have, thank you very much for your answers in the chat. Yes, so maybe more questions? Okay, so thank you very much, Dr. Ayala, for your lecture, for productive discussion. It was really interesting and inspiring. Thank you for being with us today. Yes, and
thank you very much for the nice opportunity. I'm really happy to have shared a bit of what I've learned so far.
Yeah, by the way, thank you for accepting, yes, and being with us today. I think we can finish now, yes, and we will see each other in 1 month. So stay tuned with us, and I wish you a pleasant evening.